Hey everybody, I'm Anthony Johnson and this is a Kiva system. The cool thing about a Kiva system is that it employs robots to bring product to the pickers instead of using picker time to travel around a warehouse. I've created this model to demonstrate some of the new features in FlexSim 21.2. I also want to just show you the steps I took in building it, to share how I, as an experienced FlexSim user, chose to design the various model components. And maybe you can glean some best practices from that. I should give a disclaimer here that I'm obviously not a Kiva engineer and I didn't work with one in building this model, so I don't claim to know the intricate details about how a Kiva system works. My primary source is YouTube. Nevertheless, I believe it's pretty close to what a real system would do. The data that drives the model is intentionally simplified so that I could concentrate most of the time on getting the Kiva robot motion and travel right. This video will take you from start to finish in building a Kiva model. All right, let's get started. The first thing we're going to do is we're going to add a floor storage object. We're going to give it 22 bays, I think 25 bays, 22 levels. We may change that in the future, but we'll start out with that. And then we're going to add a process flow to it. The process flow is to generate items to go into the storage. So we have a source. We're going to say 200 to start off. And then we add a create object activity. And we're going to use the box, but we're going to change its name to cart. And then we define it to create that cart object. We're going to create one for each token, so there will be 200 tokens coming in. We created a current, and we assign it to item, and we're going to give it a type of a random number between 1 and 20. So this is a simplification. Generally, you would pick carts based upon what's on the cart, but in this case, we're just going to say 20 different types of cart, and you randomly pick a different type of cart to pick from. So then we're going to change the color of the cart to be related to the type that we pick. So we use color.byNumber, and then we use that type label that we defined on the item. And then if we reset and run, it looks like it's not going in right. Let's see. Oh yeah, okay, so I must have flubbed something, but we created in the rack or in the floor storage object. And you see we've got a bunch of carts in there. So we're going to change the size of the cart so that it kind of fills up the entire size of the rack. We make the rack 2 meters tall and the box 2 meters tall. Okay, the next thing we're going to do is we're going to change the slot assignment strategy. So you want to pause the video and copy this code that you see here into the slot assignment strategy. The default slot assignment strategy, it'll pick a random slot, and then if that slot is not available, then it'll kind of find the first available slot near that. The effect is, as the rack gets bigger or fuller, it will not necessarily be random, and you'll get stuff on the outside. So this slot assignment strategy will get a more random picking of the slot. So copy and paste that code in, and you can see it becomes more random. Okay, the next thing we want to do is we want to change our flow item look so that it looks kind of more like a cart. And we also want to add some alpha transparency so we can see the robots under the cart. So I go to my flow item bin, I select that cart, and I right click and say animations or explore animations. That will show the animations window, and at that point I can set the main shape to not be shown. Then I can add shapes in the animation creator. And here I'm adding a platform that represents kind of the first shelf, and then I'm going to add 4 supports. So the idea is the cart will have 4 supports and then 1 platform. Generally, a cart will have more platforms, but for the visualization of this model, I figure 1 platform is good enough because I want to be able to see the robots under the platform easier. So here I'm creating a bunch of corner supports and placing them in their location. And I want to add, it's important here, I want to add an alpha value to that platform object. That's the main square platform. And then once I've added an alpha value, then I can set the color of the object to an alpha transparency color. If I reset my model and run, you can see that the shape has been updated. But I need to update my code as well. It's all gray, so I need to update the color. One is I'm going to add a piece of code to set the alpha transparency. But before I do that, I'm going to update the code that accesses the object. The object that I'm going to change color on is now not the main object, it's actually that sub-object, the platform. And so I access it with this adders.drawSurrogate.first accessor. That's the first object in that animations window. And I do the same thing when I set the alpha value. So I say token.item.adders.drawSurrogate.first, and that's that platform object, which is the object I want to set the color on. And I say color.a equals 0.5, so it'll get an alpha transparency. And then I'm done there. Reset and run, and you can see that I've now have these platform objects, and they are semi-transparent so that when a robot drives underneath it, I can still see it in the 3D view. Okay, next I'm going to create the process that generates orders. So an order would be a request to bring a cart out to a picker. I'm going to create a global list called orders, and then I'm going to create a global general process flow that pushes to that list. So I create a list in the process flow and I connect that list to the global orders list. And then I create a process to push to that list. So I have an inter-arrival source, and then I'm going to have it, randomly at certain points I have new orders come in. And then I'm going to assign the type of that order to just a random number between 1 and 20. Again, this would represent the type of card that I want to pull out of the warehouse. And then I push that cart or that order to the list. And in this case, the value that I push to the list is actually going to be the type itself. So I'm not going to push the token, I'll just push the type. And then when I run the model, the number that I get on that list, you'll see tokens coming in, the number that I get on the list is actually that number. Okay, next I'm going to create the process of the pick station. So I'm going to use a container because the pick station will have several objects in it. The first object that I'm going to create is just for visualization so I can kind of see the process as it's moving along. I create a queue and then I'm going to put little balls into that queue to visualize the orders that are kind of active for that station. Then I right-click on the station and I add a new object process flow. So this is the process associated with that station. I add a source to start at the beginning, and then I give it a quantity of 6. So I create 6 tokens. So what is this? This is, I want 6 active requests to be bringing stuff out from storage, active at a given time. So I want 6 at a time of Kiva robots to bring stuff out. And then as as stuff is brought out, if it's finished, then I add a new one. So I have these 6 tokens that are concurrently requesting orders. I add a pull from list, and then I create a list object that is connected to that same global list. So the other process flow is pushing to the list. This process flow is going to be pulling from that list. I get the order, and then I'm going to create this little visualization, which is this ball that I'm going to put in the queue so I can see the balls as they're active. I created in this little ball queue, this queue that I've created inside of the container. And then I assign it to token.ball. Then I change its color, the ball color, to be associated with the same color of the order that I've picked. And again, I set it on ball, and I use color.byNumber, and then I use token.type. Now I'm going to assume that type was assigned when I pulled from that order, so I need to change that so it is assigned to token.type. And then I have some delay. I'm going to fill stuff in later, but I just want some delay to actually process that order, right? And then after I'm done with that delay, I'm going to get rid of the ball in the queue. So I move it from the queue into the model, and then I destroy that ball. And then I loop back around and get my next order. So if I reset and run the model, you'll see you have in this process multiple guys waiting on orders, but as an order is pushed onto that list, this process will pull it off the list, and it will create this little ball that I can see in the queue that represents that active order. So I'm going to change around kind of the timing as to how many orders are created at what intervals, so that I can see a little bit better these balls being created in the orders list. And you can see, both processes side by side. One of them is pushing to that orders list, and then the other one is pulling from the list. Okay, next I'm going to define the process for requesting the cart, or requesting a robot to go get a cart. So again, I add a global list, and I call this cart requests. And then in my process flow, in my pick station process flow, once I get an order, I'm going to then push to the cart requests list. So I add a list to the process flow, and I connect it to the global list, and then I add a push to list activity that pushes that cart or that type to the list. The other thing I'm going to do is I'm going to add a label to the token called instance, which is a reference to the specific pick station instance. Then I'm going to add a Kiva robot, and I'm going to add a process flow to that robot. So this will be my Kiva robot process. And I start the simulation off, and then I try to pull from that cart requests list. And I add a list in the process flow and connect it to the global cart requests list. Now in this case, the value on the list is the token. But I'm going to change the query so that I get a little bit more than just the token. So I'm going to get the type and the instance. So this uses a feature of the list where if I put a select clause in the query, what that means is it will copy labels from the value, the token on the list, to the puller, which is the token that's pulling. And so in this case, I'm copying the label from the pickstation token of type and instance, and I'm copying them to the labels type and station on the pulling token. Now, this is dependent upon this feature in the list. You check this box in the list. And then next I'm going to load an item, or I'm going to find an item in the warehouse, in the floor storage. And I want to find an item that matches the type that I found. And then I'm going to assign it to token.item. So now I'm going to have a reference to an item that I can pick, and then I load that item. And then I'm going to unload the item to that pick station. I'm going to change this in the future, but for now I just unload that item to the pick station. And I want to see if this is working. Okay, next, instead of unloading the part, I'm just going to bring the part to the cart to the station, and then I'm going to wait a certain amount of time while it gets processed, while the picker picks stuff off the cart, and then I'm going to take it back into storage. So I add a travel task. Instead of an unload task, I add a travel task, and I travel to that station. Then I'm going to add a new list, which is the set of delivered parts. Again, this is kind of a synchronization point between the Kiva robot process and the pick station process. So once the cart or the Kiva robot has traveled to the pick station, then I push the token onto a list called delivered carts. It is the partition is the pick station. And then on the other side in the pick station process, I pull for that from that list. So both sides I create this list and connect it to the delivered cart, the global delivered carts list. And then on the pick station side, I pull from that list. I set the partition ID to the pick station itself, which is current. And I match the type. So I say I only pull where the type is equal to, so the type matches on both sides. And then I just want to see that that's working. So I run through. On the pick station side, it's waiting for a delivery while and this is part 8, part type 8, and it's waiting for the delivery of that Kiva robot. The robot loads it, and then he travels to the station, and then he pushes to the list, which propagates that down to the delay time for processing. Okay, so next I'm going to, after processing, I'm going to release the robot. So again, I have this list that's kind of a synchronization point called released robots. I add a kind of pass through to that list on each of the processes. And the Kiva robot will pull from that list. And again, I'm going to match by type, and I'm going to specify it on the correct partition. And it looks like I didn't put it in the right field, so. And then I loop back around. Once I'm done, then on the Kiva side, I go back around and get the next order. And then on the pick station side, I push to that list once I'm finished processing it. And I want to make sure the partition is the pick station. All right, now I think we can test. So we reset and run the model, and we kind of see it picks up a part, and then it delivers it, and that kicks the pick station process down to processing, picking off of that cart. And I want to decrease the time so it doesn't take so much time. And then once that's done, then it releases the robot, and it looks like I haven't connected up so I haven't connected it up to that list. So then I reset and run again to test it. And then it does the delay, and then it goes back and delivers, puts that cart back. And finally, I want to unload back to the floor storage. So I use an unload task. And I need to get an access to the floor storage that I loaded it from. So I have an assign labels after I find the item. I save off that floor storage to a label. And then when I unload it, I unload token.item and I unload it to token.floor storage. And then I loop back around and start with my next request. So now you should see it load it. It travels to the station, it's processed, and then it goes back and unloads into the floor storage. Okay, the next thing I'm going to do is create templates. So this is a new feature in FlexSim 21.2. I can create a template. I created a template of the pick station and a template instance of the Kiva robot. Once I do that, it's by creating a template, it inherits the same values, including the process flow, such that I just create the template, and now both the Kiva robot template instance and the pick station template instance use those same process flows. And so it's a way to scale up. Just now I can very easily add more pick stations and Kiva robots. So next thing I'm going to do is I'm going to create the A* network. So I create dividers that kind of bound the whole area. This asserts that the Kiva grid is big enough to encompass everything. And then I connect the Kiva robots to that A* network. And then I set some parameters on the Kiva system that say I don't want to travel diagonals, I want to go right angles at right angles. And then I also want to turn, I want to stop and turn in the direction that I'm going. Then I reset and run, and now you should see that these little robots, instead of traveling directly to the spots, they travel along the A* system and go at right angles. And you should see them loading and unloading to both queues, or I guess servicing both queues. Next, I'm going to define dynamic barriers in the A* system. So dynamic barriers are a new feature in 21.2 that are really useful in this situation. So when Kiva robots are empty, they can essentially drive wherever they want. But when they are loaded, they require, they're blocked by other carts that are in the storage system. So I want to add dynamic barriers when the Kiva robot is loaded and needs to go somewhere, but I don't want to. I just leave, the barriers empty when the Kiva robot is empty. Okay, so I create a group and I call it dynamic barrier management. And in that group, I'm going to create an event triggered source, and I'm going to listen to the Kiva robots on calculate path. This event is spawned, it's fired when the AGV or the Kiva robot starts a travel task and needs to calculate the path to the destination. I should point out here that you need to check the box will override return value. And because the return value of the on calculate path represents a set of barriers that you want to add. And then I set an initial label called barriers to 0. And then I check if I am loaded. I have a decision point. And then if I am loaded, then I'm going to add a custom code to calculate all of the dynamic barriers. And this is going to be all of the carts that are currently in the system. If I'm not loaded, then I just go ahead and finish. Once I've calculated the barriers, then I can finish. Now is the code that I want to write. So I call storage.system.query items, and that queries a set of items in the system. I have no query in there, so I get all of the carts that are currently in the floor storage object. And then I add this flag, which is outbound items. By default, the outbound items, or by default, query items only finds items that are not kind of currently about to leave. So I add that flag to say I also want to include those things that are about to leave. And then I go through each of the items that are returned by that query items, and I push the corresponding object to this items array. And then I set my token.barriers label to that array. And then finally, in the finish, I return that token.barriers label array, and that will communicate back to the system that these are the set of dynamic barriers that I want to add before I calculate the path. And then I run the system just to see how it works, to see that it's working properly. So when they are empty, it will just cascade through and return nothing. But then as soon as they load something, you'll notice that now that they are loaded, they will avoid and go around all of the other carts in the system by the fact that I have created that array of barriers and returned it to the calculate path. It will automatically add those as barriers. You'll also notice they kind of run over each other. So that's a setting that I set in A-Star Navigator where I uncheck that ignore inactive members box. And that'll make it so that they don't overlap each other when they're idle. You may have noticed that the travel wasn't very efficient when they were loaded. They were kind of navigating through this maze of carts. So we want to make a few changes to improve that mechanism. We have several goals we want to make. So one, we want to maximize the density of the storage, but we also want to avoid digging. So we want the carts to be available directly without having to pull carts out in order to get to them. We also want to avoid head-on collisions. So, if one cart is going one Kiva robot is going one way, we don't want the other Kiva robot to go in the opposite direction. And finally, we want to minimize travel time if possible. So I've set up this layout for the floor storage object. The black lines represent passageways, and the gray pieces represent places where you store things. So they're too deep. And I'm going to set it up so that every alternate through lane goes in opposite directions. So vertical lanes, it'll go up, then down, then up, then down. In horizontal lanes, it'll go right for one lane and then left for the other lane. So let's do that. We go into our floor storage object and we edit its dimensions. Then we're going to change the number of bays to 26 and the number of levels to 20. And then we're going to say we're going to give 3 or 6 storage areas and then 1 cross lane for going across. And then every 2 vertical lanes, there's going to be 1 lane for throughput. And we make each of those where we don't want to store stuff, we make it not storable. So we uncheck that storable slots box. So then you can see when you actually run the simulation that carts are only stored in the storable slots. Next, we're going to create the barriers, the A-star barriers. So we go to our barrier tool and then we drag a barrier out. We're going to create the vertical barriers first. So we kind of align it so that it's centered over where the grid node would be. And then we're going to change it so that one of the directions is blocked. So the up direction in this case for this barrier. And then we're going to copy that barrier across to multiple different barriers that cover every other vertical lane. So those lanes block the up direction. So you can't go up. You can go across, you can go down, but you can't go up. Then we're going to create the other one, which is we switch it and make this line so that you can't go down on that vertical lane. And then we copy and paste that lane across the different vertical lanes. Then we create horizontal lanes. So we create a barrier, we block one direction, and then we copy that to the alternating lane right there. We create a new one and switch the direction, and then copy that to the top lane as well. Now, if we just demonstrate this, if we show it, you can see on the grid now that for a given lane, you can only go one direction. You can go up, if you're in a vertical lane, you can go either up or down, but not both. And if you're on a horizontal lane, you can go either left or right, but not both. So. And then we can run our model and we can see that the Kiva robots will travel down the lanes to get to their spot. If they're empty, they'll just travel wherever. But if they're loaded, then they'll travel down the lanes. I'm going to add an additional kind of cross lane right here as well that goes the other direction so that when you come out, you can kind of go both ways. You just need to switch into a different horizontal lane. Next, I'm going to build out the route of a Kiva robot within a pick station. So I'm going to use this template instances feature. I'm going to shrink down the main pick station, and then I'm going to drag dividers into it. So I go over to a divider in the library, and I drag it into that object, and that will create a divider on both the pick station and its template instance. And then I'm creating kind of an A-star wall so that you can't go through this spot. And then I create a second wall so they can't go out the bottom area. Again, I drag it into the pick station. And so then it's inside of that pick station. I'm going to have one entry spot and one exit spot. I drag a one-way divider in so that you can only get in through this left side. And then another divider that will only let you get out through the right side. And I manually enter some of the coordinates for these points on the divider. And then I'm going to create another instance so I have 3 different pick stations. and I'll drag it out. So now I have 3 pick stations, and I can reset and run my model, and you can see that they only get in through that specific spot. So when I created that, I realized that the size of the pick station entry and exits area kind of conflicts with my, on again, off again, or up and down routing. So if you look, the routing is such that the entryway would be across or different than the direction that the AGVs would go. So I'm going to extend this pick station out to be 1 wider than it was. So then it's 6 units long. All right, I want to make some adjustments to the travel mechanism. You may have noticed that they don't actually travel all the way to the object. So I want to adjust that. The way I do it is by traveling to a location instead of an object. So if I travel to an object, it just travels to kind of the fringe of that object. But if I travel to a specific location, then it will travel directly to that location. So here I'm swapping out a travel to object with a travel to loc, and I travel to the station's X, Y, and Z location, which is right at that corner of the station, or of the pick station. And then if I reset and run the model, we should see that it travels directly to all the way to that pick station location. All right, the next thing I want to do is I want to just shrink down that pick station so it's visible, so make it black, but make it kind of smaller. And then I'm going to create another template instance to go all the way across the bottom row there. So I'll have 4 pick stations. And then I want to create a bunch more robots. So I just have a template and an instance at this point. So to do that, I can just copy one of the instances and paste it, and that'll create a copy of it, which is also an instance. And then I can paste a lot more. And then I kind of rearrange them, put them kind of at a reset spot for each of them. And then I can reset and run the model, and we have lots of Kiva robots going in and fulfilling picking orders. Next, I'm going to work on prioritization of assignment of Kiva robots to the pick stations. You may notice that the Kiva robots kind of are assigned to, one pick station, 1 or 2 pick stations, and the other pick stations are starved. So in order to fix that, I'm going to adjust the Kiva robot process and the pick station process. So I'm going to keep track of how many Kiva robots are assigned to a pick station. And then when a Kiva robot takes an assignment, it's going to prioritize those with the fewest assigned robots. So I add an assign labels to the pick station, and I say assigned robots to 0. Now, there's 6 tokens here, but they're all going to assign it to 0, so we're good. And then for every time I get a cart, or I get an order, I increment every time I get assigned to a Kiva robot, I increment this label of assigned robots by 1, so that I now have, 1 or 2 or whatever robots assigned to me. And I need to make sure that I assign it on current and not token, so this is the pick station. I increment the assigned robots, I wait for delivery, and then after I am done with the picking, then I decrement the number of assigned robots right before I release that robot. So I use the increment label pick option and hit -1, and that will decrement the number of assigned robots. And then once I've done that, I go into the cart request and I order by the value.instance.assigned robots. So the value is the token. The token has a label on it called instance, which points to the pick station, and the label assigned robots is on the pick station. So value.instance.assigned robots, and I order by that ascending, so I take the lowest value first. Okay, when we run the model, we'll notice that it's still not doing it in the correct order. This is because of the initial ordering of the tokens in the pick station. Each pick station creates 6 tokens. So what I'm going to do is I'm going to add a small random delay after I create the initial tokens, so that some of the tokens will delay a little bit longer, some of the tokens will delay a little bit shorter. It'll still be a very small time, but that means that the time at which they jump into that poll to get their first order will be somewhat randomized. Okay, so I'm going to use a uniform distribution between 0 and 0.001. And I just want to show you the difference of what this makes. So if I have it out, if I take that activity out, and I look at the back orders of the orders list, you'll notice that it's completely ordered. So pick station is the first 6 tokens, pick station 1 is the second 6, pick station 2, and so forth. Which means that the first order that goes on, the first 6 orders will be pulled by pick station 1, the second 6 will be pulled by pick station 2, etc. However, when I put that delay back in and look at the back orders, it will then, you'll see that the back orders are somewhat random. They're randomized because I've put that delay in, so the time that they get onto that back order list is randomized. This is only kind of a side effect of initializing the model. So it wouldn't be an issue later on in the model, but when you first start your model, the ordering of those guys getting in has a difference. But then when we run the model with that randomized set in, we can see here that the Kiva robots do kind of distribute themselves across the different pick stations. I want to work on some glitches now. So one of the things you'll notice is they kind of overlap each other. This is due to the deallocation time. So to change that, I go into the A-star navigator and I increment the deallocation time offset, so that it'll take a little bit more time before it deallocates a given cell in the accumulation algorithm. The other issue is sometimes when Kiva robots don't have anything to do, they just sit there and they kind of clog up the area. And finally, the third issue is if you have these head-on collisions, then they have to kind of reroute around each other, which can be inefficient. This is specifically for empty robots. Recall my previous one where you had these alternating up and down sections. I'm going to supplement that with a up and down or alternating sections for the empty robots, so that even when you're empty, you kind of alternate based upon where you alternate between going up and down. This will avoid these head-on collisions. So first let's work on the idle process, so what to do when you're idle. So I'm going to extend the Kiva robot process a little bit, so I'm going to give myself a little bit more room. And then I'm going to, as soon as I start, I'm going to save the home location of that object, so the location where I started out. And then I'm going to take that get cart request and I'm going to make it into, instead of like wait until you get your next cart request, I'm going to try and get a cart request. And then if I can't get a cart request immediately, then I'll travel home and wait and then get a cart request. So I have try get cart request, then travel home if I don't. And I'm going to travel back to that home location. And then I need to check the use max wait timer, and then when it expires, I release the token to connector 2, which is to that travel home. Then finally, I'm going to copy and paste this try get cart request, and I'm going to put it right after the travel home, meaning I travel home and then I get a cart request, and I don't, or at least I wait. It's not a try anymore. I'm going to just wait until I actually get that cart request. And around got exceptions. Looks like I used the wrong label name, so. So then if I run the model, they should do their job, but then at certain points, you should see these robots kind of traveling back to their home location. And I'm going to later on adjust how they get into their home location because it looks like they're running into each other, but I'll do that later. So the next thing is the empty robot kind of traffic rules. And so I create a pattern barrier, and I kind of use a trick where I split up the pattern barrier into one pattern per horizontal cell, okay? And I count the number of cells, and I make sure that it's a power of 2. So I'm counting to 16 here and making sure that the distance above is 16 cells, and then the distance below is 4 cells, which is a power of 2. And then once I've got that nice and neat, I can then just split them. Because they're split in half, I'm actually splitting them by powers of 2. And so when I split them into 16, each one of the patterns is exactly 1 cell wide. And then I go in, and each horizontal row, I alternate the direction that is blocked for that row. So for one, it can't go left. For the other one, it can't go right, and so on down the line. Now eventually I'm going to extend this and kind of place it over the top of this floor storage, but for now I'm going to kind of leave it out to the side while I build the other one. So I build that was the vertical one, this is the horizontal one, so again I kind of do the same thing. I stretch it out across the width of that floor storage object, and then I split the patterns into powers of 2, so I count up to 16. So that's 16 right there, and then I count up to the right, and there's 10, which means I'm going to split it up into 8 long, and then another 2, so each of those is a power of 2. And then once I do that, I can kind of split it all out into each individual one so that each one is exactly 1 cell wide. And I alternate the directions on this one. They're going to both be dragged over the top of the floor storage. When they overlap, they act like a mask. So it applies the blocked direction for each of them. So if one is blocked going down and the other is blocked going to the left, then that cell will be blocked going both down and to the left. And then I'm going to add a conditional rule. So these only apply to the empty robots. I don't want this rule applying to the loaded robots because they need to get into the cells to load and unload their carts. But for the empty robots, I only want them traveling along these kind of lanes. And I stretch it out over the width of the floor storage. Now it's kind of tricky here. You have to kind of fudge with it so that you can still grab them when they're right on top of each other. Sometimes it's hard to grab the right one, and so I'm trying to create like this kind of jagged edge that still covers the floor storage object correctly, but has a little bit of an offset from each other so that I can grab the objects individually. And I make a few mistakes because you shouldn't be scaling one of the directions. And then I go to my A-star navigator and I hide the barriers so that I don't see them. Next, I'm going to address an issue that happens relatively seldom, but it still does happen, so we need to address it. So you'll remember when we added dynamic barriers, we added them for all carts in the system that are both stored and are outbound. We did not include carts that were inbound. So there are some cases where you build your path based upon what's in the storage system, and then before you traverse a given cell, a cart is placed into that cell so that it now blocks your path. So we're going to add a new mechanism that listens for these entries and sees if that given entry will block the path, and if so, we route around it. To create this process, I add a wait for event activity. I'm going to wait for the floor storage's entry activity. The floor storage is pointed to by the token's floor storage label, and I listen to the on entry. I'm going to assign the item label on the token to the item that is entering. I only want to have this process, this listening process, happen while I am doing a loaded travel operation, which means I only spawn that process right before I start a loaded travel operation, and then I'm going to kill the process after I'm done. Once the event happens, I do a breathe to allow whatever logic in the floor storage object is happening to finish. And then I add a custom code to check if the path is blocked. And what I do in here is I add a dynamic barrier that's based upon that item that just entered to the A-star navigator. And then I check if my current path, my travel path, is blocked by calling an isBlocked method on the travel path. After that, I remove the barrier that I just added. And now once this code has run, I have stored on this token label isPathBlocked a value of 1 or 0 as to whether or not that item that just got placed in the floor storage just blocked my path. Then I have a conditional decide. If the path is blocked, then I can't immediately preempt the object. I need to wait until it arrives at its next cell. So if I preempt the object immediately, then, and he's right in between, traveling between two cells, then he'll kind of jump when he gets preempted. So I want to wait until he arrives at his next cell. And so this for loop is searching through the travel path and finding the first entry in the travel path where the arrival time is greater than the current time. And then I wait for that amount of time. And if the traveler is already blocked, then I just say don't wait at all. So now that I have waited the amount of time to get to my next cell, then the next thing that I do is I preempt. Now I could preempt through process flow. I'm just going to write a piece of code that creates a task sequence. I create a task sequence and I give it a priority that is one more than the priority of the robot's current task sequence. So this will ensure that it does preempt. And then I add a task to that task sequence, which is break. And I break to the robot's currently active task sequence, which is I preempt and then just tell him to start that task sequence over again, or that travel task over again. I add the various labels to the connectors so that I can see the flow a little bit better. Again, I need to make sure that I only run this process while I'm doing a loaded travel task. So I spawn the process before I do the loaded travel, and then I kill the process after I'm done with that travel. And I want to do the same thing when I travel to put the cart back into the floor storage. So the first spawning of the process happens once I've loaded the cart and I'm bringing it out to the picker, and then I want to respawn the process again when I put it back into storage, and then kill the process once I'm done traveling back into storage. The other thing I'm going to do is I'm going to split my travel task back into storage into two different tasks. There's going to be a first task that does a place offset, which is like an unload without the actual unload. It'll do the travel operation to the position, but it won't finish the unload. And I'm going to do the place offset, then kill the listening process, then finally unload. This is so that the listening process doesn't actually listen for the unload of the item that I'm actually unloading. And when we run the model, it should work properly. Although I do, as I look at it, it looks like there's a few tweaks. I need to make sure in the spawn entry that I say parent label access is read only, because I'm sharing that item label, or at least I'm reusing that item label on the token, and I don't want that item label to be written to the parent process or parent token. For the rest of this video, I'm going to be making visual improvements to the model to make it just the animations look better. So the first thing I'm going to change is you'll notice as the Kiva robots rotate, the carts rotate with them. This doesn't happen in real life. Generally, when the Kiva robot rotates, the cart stays stationary. So I add an on pre-draw trigger to the Kiva robot. Make sure that you do it on the template so that it will be applied to all of the instances. And I add an on pre-draw trigger to that robot, and in that on pre-draw, I essentially just set the rotation of the first object in there, meaning the cart, to the negative rotation of the robot. And then if I reset and run and show that, we should be able to see that as it rotates, the cart stays stationary as far as its rotation goes. However, it does kind of move because I haven't set the position correctly. I go back in and I set the location of that cart, and I set it to the center of the Kiva robot, which is half of its X size, negative half of its Y size, and then its base will be 0. And the set location method has a second parameter that you can take that says where relative to the cart do you want this location to be, and it's going to be halfway in to the size of the cart. So that if I reset and run, the cart should, when they're loaded, we should see that they rotate, or at least they stay stationary as the Kiva robot rotates. The next thing I'm going to do is, in real life, when a Kiva robot loads a cart, it does this corkscrew action where it spins around, and that action is essentially lifting the cart up. So I'm going to add some kinematics to this process. I split the travel into a pick offset followed by the load. The pick offset is like a load without actually moving the cart in. So I have two different tasks, a pick offset and then a load. And between those two tasks, I'm going to add some kinematics. I do a create kinematics activity and then an apply kinematics activity followed by a finish kinematics activity. The apply kinematics activity is the critical one where I say rotate 720 degrees and I rotate over 5 seconds. In other words, the rotational speed will be 720 degrees divided by 5 seconds. And if I run that model, you should see now that when they load their cart, they do a spinning action. And I want to do the same thing for when I unload the cart. So I'm going to copy and paste each of these kinematics activities. And in this case, I rotate negative 720 degrees. So if I reset and run the model, you can see when I unload the cart, it will rotate, it'll spin around 720 degrees. You'll also notice that the cart's rotation is incorrect when it's placed in the floor storage. This is because its rotation is whatever the rotation was set to the last time the window repainted. So instead of leaving it that way, we want to explicitly set the rotation of the cart right before we load it into the floor storage. And that will fix that issue. Next, we're going to work on the visuals for the pick station. So two things I want to do. One, I want to put an operator at the pick station so that a person looking at the model can see, oh, there's supposed to be a person here who's actually picking. It doesn't have functional relevance to the model, but he is a visualization to see what's happening when certain things are being picked. And the other thing I want to do is change the ball so that the ball becomes more prominent when the pick operation starts for that ball. So I changed this delay, I changed the name of the delay to say perform picking. And then before I do that, I want to move the ball up. So I set the location of the ball to its XYZ location, but I increment the Z location by a certain amount. So he'll just pop up into the air. And then what I want to do is I want to run the animation on this operator that I've dragged into the pick station. So I say run animation, I add a run animation activity. The object is the object named operator inside of current or the pick station. And the animation is going to be named open. This is one of the standard animations that comes with the operator that kind of looks like a picking operation. Then after I am finished picking, I add a change visual activity that stops that animation. Again, it's the operator and the animation is the open animation. And I reset and run to test. And it looks like I have not put the right label name, so I changed the label name to ball. And if I look, looks like it's not doing it correctly. I may have picked the wrong option. So I'm going to go in, remove that option, and choose the set location option. And that lifts the ball up, and you can see as the cart arrives, the operator runs this little animation as if he's picking. And that's our model. Hope you've enjoyed this tutorial. Thanks for listening.